This is section 7.1, differences to find equations. Here's the example we're going to work through. It models the relationship between the number of sides and the number of diagonals of a convex polygon. Use the function number of a dodecagon, a 12-sided polygon. This problem uses some geometry terms which you may not be familiar with, so let's kind of explain those as we go. First of all, if we are going to use finite differences to find out the polynomial function we need, we first need to come up with some sort of data, some x and y values. Tell us in this problem that the x will be the number of sides of the polygon. Let's create some examples. Right, so if we have a triangle, the triangle has 3 sides and it has 0 diagonals. You may remember that a diagonal connects like opposite vertices, opposite points. If we have a second example like a quadrilateral has 4 sides. A quadrilateral has 1, 2 diagonals. So 4 sides and 2 diagonals. Next we would have, after a quadrilateral, we would have a pentagon. So 1, 2, 3, 4, 5 sides. So 5 sides. And let's see, 1, 2, 3, 4, 5 diagonals. So 5 diagonals. Okay, so next we have the hexagon. 1, 2, 3, 4, 5, 6. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it, 9 diagonals. So wait, 6 sides first, and 9 diagonals. Okay, so basically what we've done is we started to get some data with some information that we can use. So the number of sides will be the x, and the number of diagonals will be the y. So let's actually create ourselves a little table here. Let's actually erase our pictures, our diagrams, and we'll make ourselves a table. And this table, let's make it vertically. So let's do this. Let's move this over here. Let's move this over here, and let's make our table like this. X, Y. We have 3 sides. We have 5 sides. We have 5 diagonals. We have 6 sides. We have 9 diagonals. And if we actually kept going, coming up with some examples, we could actually see that 7 sides, a heptagon, has 14 diagonals, and an octagon with 8 sides has 20 diagonals. So this just gives us a couple more points to use. So now that we have this table, we don't need this information, and now we can apply our finite differences to find out what degree polynomial function we're going to want to create. So here we go. So first, 0 to 2. 2 minus 0 is 2. 5 minus 2 is 3. 9 minus 5 is 4. 14 minus 9 is 5. 20 minus 14 is 6. So our first set of differences does not give us a constant. So now let's go to our second set. Obviously, 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. And 6 minus 5 is 1. So there is where we see our constant difference. And we know that whenever the second finite difference gives us a constant value, that means we have a second degree polynomial or a quadratic. Now that we know our polynomial function will be a second degree polynomial and that that's a quadratic, we're going to use our calculator to run what we call quadratic regression. So the first thing you're going to do is the stat button, and you're going to want to edit the list L1 and L2 with the data that we have. So let's hit enter on edit, and we see L1 and L2 here, and you can see that our data, our X and Y, that we started with way over here is already entered into our calculator. So the X is L1 and the Y is L2. And now we can run what we call quadratic regression on that data. So hit the stat button again, and we're going to go over to calculate. And we know it's a quadratic, a second degree polynomial. So we can go down to number 5 and we can run our quadratic regression. Now the calculator will automatically run the quadratic regression on L1 and L2. And so we're going to hit enter here, and it's going to give us the quadratic that is our polynomial function. So we have the quadratic y equals a is 0.5, x squared is negative 1.5 x plus c, which is 0, so we really don't even have to write that down. So now we have our polynomial function y equals 0.5 x squared minus 1.5 x. And we can use this function to find the number of diagonals of a dodecagon, which is what they're asking us to do in the problem. So let's do that. So a dodecagon has 12 sides. X stood for the number of sides, so let's plug in 12 for x. We can throw this into the calculator and we can figure out that y ends up being 54. So a dodecagon has 54 diagonals. So this is an example of how using finite differences led us to understand what degree polynomial function we would use, which allowed us to then use the appropriate function on the calculator, quadratic regression, to get our polynomial function. Now, of course, if our first set of differences here would have resulted in a constant value, then it would have been a first degree polynomial, and we would have run linear regression on the calculator. If it took to the third set of differences to give us a constant value, then that would have been a third degree polynomial, and we would have run cubic regression on the calculator.